Okay, we want to talk now about storing variables. He says that when your computer, the memory is sort of the most limited resource, he says. In other words, that's the thing you have to worry about the most on your computer. The hard drive, you have lots of space, but memory is more limited. And these days not so much true, but still it's true. In the past it was more true. Okay, so we want to talk about the way that computers store things. And I talked about this a bit before, but this is a slightly different description of it. So we want to talk about what's called the binary number system. And what it means is that everything is basically just a pattern of zeros and ones. And I mentioned this in class before. I mentioned it, I said that if you have one digit and you can only display a 0 or a 1, then you have two possibilities, 0 and 1. If you have two digits and each of those can only display a 0 or a 1, then you have four different possible sequences that you can construct. You could have 0, 0, you could have 0, 1. So if you have just two slots or two digits, you can have 0, 0, 0, 1, 1, 0, and 1, 1. So that's four possibilities. If you have three, I should have put this over here, oh well. If you have three, the third slot there, then with all four of these, you could have zeros here, or you could have ones here. So in other words, you have two sets of these four here. So you have 8 possibilities. In other words, you could have 0 here. I can't do this. 0, 0, 0. And then you could have 1 with 0, 0, 1 with 0, 1, 1 with 1, 0, and so on. So you could have 8. So it's, if you just have one slot, you have two possibilities. You have two slots, you have 4 possibilities. 3 slots, you have 8 possibilities. 4 slots, you have 2 times 8, or 16 possibilities, and so on. So he says computers use binary. That's what I was just using. That's called binary. That means that whatever you store in a computer must be expressed as a binary pattern of ones and zeros. So suppose you want to, so now they say, how do you write 27 in binary? In binary code, this number is actually like this. Now we'll see that in a minute. Each digit referring to a power of 2. The diagram in figure 314 shows you how to represent 27 in the more familiar base 10 format. And then in binary, binary is also called base 2, and we use what we call, normally we call that base 10. So this is base 10. So in other words, when I write 2, 7 to mean 27, what do I mean? I mean we have 7 ones and 2 tens, right? That's what 27 means. 2 tens and 7 ones. So what we're saying is that the first digit is the ones digit, the second digit is the tens digit, the third digit would be the hundreds digit, the fourth digit would be the thousands digit, the fifth digit would be the 10,000 digit, and so on, right? So so we say that 27 is 2 tens and 7 ones. So that he says in base 10 each digit represents a power of 10. Right? The first digit represents the 0th power of 10. The second digit represents the first power of 10. The third digit represents the second power of 10, and so on. To find what number the pattern base 10 digits represents, you multiply the relevant number by the power of 10. So 7 times 1, 2 times 10, and so on. And then add the results, and then add these, and you get 27. Now base 2 would mean that instead of powers of 10, this is called base 10, base 2 would mean instead of powers of 10, you use powers of 2. So you have, instead of 10 to the 0, you have 2 to the 0 is what, so if you have a 1 here, that means 1 times 2 to the 0 means 1 times 1. If you have a 1 here, it means 1 times 2 to the 1, which means 1 times 2, because 2 to the 1 is 2. And then the next digit would be the 2 to the 4th power. The next, 2 to the 2nd power. Next would be 2 to the 3rd power, 2 to the 4th power, and so on. So if we write this number, 1101, 11011, 11011, what does that equal? It means 1 times 2 to the 0, which is 1, and then 1 times 2 to the 2, 1 times 2 to the 1, which is 2, and 0 times 2 to the 2nd, which is 0 times 4, which is 0, and 1 times 2 to the 3rd, which is 8, and then 1 times 2 to the 4th, which is 16. So what do we get? 1 times 16, 1 times 8, 1 times 2, 1 times 1, we add them up, and it gives us 27. So that means that the way that we would write 27 in base 2 would be 11011. In other words, this in base 2 is equal to 27 in base 10, we say. Now, the sort of important thing about base 2 is that we only use 1s and 0s in here. Whereas in base 10 we have to use, we can have 0s, we can have 1s, we can have 2s, we have 3, 4, 5, 6, 7, 8, 9. 10 different digits actually. 0 plus 1 through 9 is 10 different digits we use. But when we're talking about base 2, we only need the digits 0 and 1. And so that corresponds to basically whether electricity is flowing through a circuit or not. So it's just yes or no, 0 or 1. So that's why we use base 2. He says, although this may appear to be a bit obscure, note what is happening. In base 10, the decimal system that you're familiar with, each digit fits into a slot. This slot represents a power of 10. The first representing 10 to the power 0, the second 10 to the power 1, and so on. If you want to know what number the pattern represents, you take each slot in turn, multiply it by its value, the value it represents, and add. Okay, we said that already. The same applies to binary. It's just that you're not familiar with dealing with base 2. To convert the number back to base 10, you take the digit. We did this already. Okay. Now, I also talked about bits and bytes in class. In computer terms, a binary slot is called a bit. So a slot that can be either a 0 or a 1 is called a bit, a binary slot. It is the smallest possible unit of information. So a single slot is the smallest possible unit of information. In other words, a bit is the smallest possible unit of information. The answer to a single yes-no question, represented by a part of the computer's circuitry that either has electricity flowing in it or not. So if electricity is flowing in it, it might be yes, and otherwise no. So that's the way the electrical pattern in the computer gets translated into a binary system, or a binary representation. So we can create these numbers based on whether electricity is flowing through billions and billions of little circuits. The reason why there are 8 slot bits in the diagram in figure 314, there are 8 slots or bits here. Why is that? Is that there are 8 bits in a byte. So remember, we talked about this before. We said that a byte consists of 8 bits. So why should we define it that way? It's just a convenient way to, I guess it's just historical reason, or it's just convenient. So we talk about 8 bits. We want to use units of 8 bits, so we call 8 bits 1 byte. A byte is the unit of measurement that you use when talking about your computer memory. For example, we have gigabytes or kilobyte. A kilobyte is 1024 bytes. It's kind of weird. A kilo should be 1,000, but it's not 1000, it's 1024. Use 1024 rather than 1000 because 1024 is the 10th power of 2. Okay, the 10th power of 2. If you go back up here, this is the 7th power of 2, but if you went to the 10th power of 2, it would be equal to 1024. The 7th power is 1028. So far as the computer is concerned, it's a round number. So, you know, we usually want to talk about round numbers like 1000, but for a computer, really 10,024 is more of a round number than 1000 because 10,024 is a power of 2. Computers don't think of things in terms of tens like you do, so 1024 is more natural to a computer than 1000 is. Likewise, a megabyte is 1024 kilobytes, or this many bytes. So a megabyte is not 1000 kilobytes, but actually 1024 kilobytes. So we have 1024 bytes is a kilobyte, and then if we take 1024 of those, we get a megabyte. And that's actually this many bytes, because it's 1024 times 1024 gives you this. Again, that is another round number. It doesn't look like a round number because this is the 20th power of 2. A gigabyte is 1024 of megabytes. Again, think 2 to the power of 30 and you're on the right track. Finally, a terabyte. Okay. And a petabyte. He says, so what's the point of all this? Well, having an understanding of how computers store variables helps you design your programs better. Suppose your computer has 256 megabytes of memory. Well, that's very small, but this was written in 2010, or for Visual Basic 2010, so that was maybe appropriate then. Anyway, that's this amount of kilobytes, or this amount of bytes. Multiply 8 by this. Okay, multiply by 8, and it's that many bits. So multiply this bytes, multiply that by 8, because there are 8 bits in every byte, and it's this many bits. So it's this many zeros and ones. This many zeros and ones. What is this? 2 billion something. As you write your software, you have to make the best possible use of this available memory. Okay, let's continue with this in the next video. We'll talk about how to represent numbers, but we sort of did it already. But we'll explore this a little bit in a little bit more detail and make sure that it's clear.